Today, according to the tentative schedule, we're gonna cover the grinder and the saw, and if there is enough time, I'm gonna throw in some threading in there. Just because we were supposed to be we were supposed to talk about threading when we had the class about the lathe, and I don't think we were able to do it. Surrender. All right. So the grinding that we have is a pedestal grinder, right? So like but it's just about like a. So if you got a bench grinder and you put a pedestal, then you get a pedestal grinder. So like not. I don't even see that as a difference, but there it is. Or it could be like a portable grinder or an angle grinder. So like we're gonna be using both, right? So hazards involved in the grinding. So grinding on the side of the wheel. So if you look at the grinder, we never grind on the side here for two reasons. It's easy for whatever stock you're grinding on the side to get caught. And also, if you grind it on the side, you're gonna change the structure of the wheel. So the wheel is true or round or square, and we call that true because all the mass here, the mass all over is actually the same, right? As soon as the mass on one side is smaller than the mass on the other side, then we're gonna start having vibration, right? Why? Because there's more mass on this side, and all of a sudden this mass is actually going to go up and then down and then up and then down. So that's what's going to cause vibration. So if you have a grinder at the farm and the grinder is like walking away, we always think about, there's something wrong with the grinder, and the problem is actually the wheel itself, right? So let's see. So we never grind on the side. Applying work too quickly to a cold wheel. So for those who are in the welding station, you guys saw that, or we covered that when we start the wheel, we step to the side for like a minute or so, or 30 seconds. We say a minute just so like we just don't go straight up and start like actually hitting the wheel. We turn it on, and then we just like wait for a little bit, and we try to stay away like from the line of fire that's like a straight in front of the wheel. So if the wheel is not in good condition and it's gonna crack and explode, then we can actually we don't get hit, So let me write here, wheel explode. I'm gonna try to find a video of a wheel exploding just so you guys see what would happen in that case. Grinding too high above the center of the wheel. So I believe that like for everybody that we're already in the welding station, at least for one meeting, it's pretty much the same that we're going to talk here today. So it's going to be kind of boring, but that's what we get, right? So any wheel or any cutter, it's always going to push the teeth against the rest, right? Always. So in this case, when we try to use the grinder, we have to use the rest to rest our workpiece there. What does that mean? Or why is that? Because the wheel is actually going to push the steel down, and if actually my steel is actually touching the rest here, it's actually gonna transfer that force to the rest. So actually, it's not that you are holding it, like you're just moving around, but you don't have to actually hold it in a way that like you have to prevent it from going down, right? So if somebody grinds too high above the center of the wheel, guess what? Your hand is actually going to actually have to hold this force now. See? So that's a lot more unstable, right? So we don't grind above the center of the wheel. Dressing the wheel incorrectly. So first we're going to talk about like addressing the wheel. Dressing the wheel means if my wheel here is in two conditions. Either the wheel is not square, that means I'm gonna look at this on the top, right? So here's my rest. Here's my wheel. So the wheel is supposed to be as close to the rest as possible. OSHA says 1/16. We say as close as possible. Why? Because if you're grinding a 1/16 piece there's a chance that you're going to get caught, right? So you want this gap here to be the smallest as possible, right? So sometimes you get, let's say, a guy would come and try to grind a piece of aluminum on the wheel. This is actually the most common material that we grind on the grinding wheel in a way that the wheel that's clogged. So if I grind like a aluminum here, aluminum is so soft that a lot of the aluminum is gonna get caught on the wheel, right? You're gonna see like this shiny thing on the wheel. So what do I mean getting caught? So if I actually zoom in into this, you have all these little ridges. That's the grit, right? It's what actually grinds, and the aluminum is gonna get stuck here just because it's so soft. So that's why you see like all these shiny pieces there. So to dress, we use, this is the tool that's called the dresser. If you look on our grinder there, we have one exactly in that same spot, right? The dresser, so it has the handle there. Let's see. And here in the front, you have some wheels that what it does is actually to take material from the wheel. So when I dress, I put it against the wheel and I push the dresser against the wheel. For those who were in the welding station, I do that in the first day. You push it against the wheel and you're gonna see like a bunch of dust coming out. That dust is actually all the material that makes the wheel coming out from the bind, because it's just like a bunch of like a sand particles with like some glue to bind it together. So as soon as you dress it, you are breaking off that sand. So if I come in here and I see that um, that this aluminum is only on one side of the wheel, I might think, I'm gonna dress the one side that has a bunch of aluminum on it that's clogged. So when I dress it, I'm gonna come in, I'm gonna apply my dresser on this side. So what am I gonna get? I'm gonna get this. This side is gonna be a little shorter. Oops. All right, because I only dressed one side. That's not the correct way of dressing. Why is that? Because I'm gonna just start that same one here on the side. So this was how it was supposed to be, and this is how it is, right? I'm gonna actually put my rest as close as I can to my wheel. But now, this area here is actually a gap. Even though my wheel is as close as I can to my rest, I still have a gap that's too big on that side, right? When I'm actually grinding here, it's safe to grind on this side, but it's not safe to grind on that side. We don't want that to happen. So in case we have too much aluminum on one side, or we have to dress the wheel, we always have to dress the wheel flat. Oh, but then we're gonna need to buy like another wheel soon. It doesn't matter, you know. It's what has to be done. So that's why it says here, if you dress the wheel incorrectly, most likely you're gonna get yourself in a condition that's not very safe, you know. So the next one is actually crack and flaws on the wheel. So when you go to use the wheel or to use the grinder, we don't know much about it. Like we don't know if somebody was actually messing up with it and actually made a mistake 30 minutes before you got there, you know. So even if you come in and you say, Rodrigo, I want to do some work in the morning, and then you do the work in the morning and say, I have a class right now, and I'm gonna come back like a 50 minutes from now after my class is done, and I'm gonna say, yeah, come back. You come back, you don't know if there was anybody there. So you have to consider like the same precautions that you had to start the day is the precaution that you have to have even if you go to the restroom and you come back. You know, we have to go and kind of like have a quick inspection, and that sometimes what's going to cause the problem is something like this. You step out to go to a class, and I'm working there in my office, and then you come to me and then you say, did anybody go in there and work on the grinder? And I'm gonna say, no, I haven't seen anybody there. Then you start doing the work, but I wasn't really paying attention to the station, so I don't know what happened. But I gave you the best information that I had. So sometimes people trust on some information, and the other person wasn't lying. The person just didn't know, and then you put yourself in a condition that's not the safest, you know. So you step in, you step out. As soon as you go back in, you have to actually consider, somebody might have messed up with that, right? I saw like I don't know if it was that group that we were actually cutting something on the code saw, and the guard was actually stuck. So we were trying to actually see what was wrong with the ground, like with the guard. And all of a sudden, when I was able to lower the guard and get like a from the stuck condition, a piece of steel came out from behind the guard. So like that's a condition that it could have happened between, like, I don't know, 10 minutes, somebody go in there, cut something, and it's ready, and then now the guard is stuck. You have the machine running. You say, oh, this guard is stuck. You try to move the guard. That piece would actually be released from where it was. It could actually hit the wheel and hit you. So it was 1 second. So we always consider use we inspect everything before starting the work. Once we think that's safe, we can start the work. We step out, we have to inspect it again. You know, even if it's like a basic inspection. So the next one is actually run a wheel too fast. When is that going to happen? So let's see. If we look here on the grinder, so let's see. We have the motor there. So that's the motor. And we have a shaft coming out this way. Right? So what we do is we install a wheel around it. And then someday I say, we need to replace this wheel. And then I don't know what are the specs of the wheel. So I'm going to say, I'm just going to buy any wheel that has the diameter of the shaft the same. Then you can go there and buy one. The problem is some machines, they have different max RPMs. So you have to actually match the max RPM from the machine with the max RPM from the wheel. Because when they build the wheel, the max RPM is so the structure is still stable under that max speed. As soon as I go beyond, it's not that the wheel is going to explode right away. It is, I don't know what's going to happen. And the problem with I don't know what's going to happen is I'm going to start, we can start using the machine and we step to the side. We say, let's run it for 5 minutes. It runs for 5 minutes. It's fine. And then you start using it, and then it explodes. That's a condition that as soon as you don't match the specs between the wheel and the grinder, you don't know what to expect anymore. Now you can get comfortable because that first 5 minutes it was working fine. So you get comfortable. You were I'm safe now. I can get closer. I can actually pull the guard off. I can, so once you get comfortable, now you start putting yourself sometimes in a dangerous condition. So that's why we always have to match the max RPM because of the wheel with the max RPM of the machine. And this is especially going to happen with angle grinders. You go and you see like that the shaft is the same size. You think it's for the same machine, but it's not. So we have to actually watch for every single equipment. But in this case, with grinders, it's gonna happen more often with angle grinders. Right. Flanges. So something that happens that's actually very common. Let's see here. If we can zoom in enough. Okay, I'm gonna just like erase all this. Then we're gonna start over. All right. So if we look at the grinder here, we have the shaft that's coming out, right? We have the wheel that we're going to install around it. And what else? And then now we have to secure the wheel like where it goes, right? So now I'm not gonna, so you have a nut, right? To install there because they have threads on the end. If you install the nut there, there's gonna be too much pressure applied to a small area of the wheel. And sometimes there is like so for example, that actually happened with our the grinder that we bought from Harbor Freight. It had just a washer here. But the rule says, what the rule says. The flange, the lack of flange, the unequal size of the flanges, or flanges that are less than a third of the diameter of the wheel. So the piece that should go here is technically not a washer, the one that goes between the nut and the wheel. So this piece here is what we call a flange. We have to have one on each side. It's actually something like this. We have the wheel, then we have one on the other side. And then we have, so this is the shaft, and this is the nut. So sometimes you are going to install it and you forget this one. So now you have only one. So now this guy is sitting like this. You get this tight. You force this hole here, the center, to actually to expand. Again, it's not designed to work like that. So you just put yourself in a condition that's not stable. It might work for a day, 2, 5, but you just put in this like a condition that you don't know what's gonna happen, you know. So we have to follow the rules of we need flanges on both sides. We need the flange to be at least a third of the diameter of the wheel. So we can, so the pressure that we put against the wheel actually is applied constantly to a large area, right? I'm saying this, and I don't expect you to actually go there and evaluate our stuff, but you can too, you know. But this is actually, so like a, for example, if you go to a big manufacturing plant, there is a guy that's a specialist on OSHA stuff that goes and evaluates every single equipment. Most of the problems that happen with things that are simple like this would happen in a farm, you know, or we happen at home for a guy that does that as a hobby, you know. So we have to watch for like a, not only when we're at work, but also when we're just like a using it for fun, or at the farm. Or and this is another one that's very similar problem: storage of the wheels, or even I would say condition and storage of the wheels. Imagine you have a grinder at home, you need a new wheel, you go to an auction, there's a guy that's selling all their stuff, or go to a garage sale, you buy a wheel, the diameter is the same, you match, so the diameter is the same, you match the RPMs, and then everything is correct. But now you have to consider what's the condition of the wheel. It wasn't new. Even for the new ones, like I would have like a, always inspect and try to understand. So the condition when you get it, and the storage of the wheels, because you don't know if the guy stored it correctly. For example, this is a major one. And in North Dakota, this one is a very important one too. Not as important. This is not as important here in Brazil, because like we don't get anything below 50. But here, this one is actually one that's very important. The humidity. Why? Because the wheels, as I said, is actually a bunch of like a sand bound together with like some resin, As soon as we have all the humidity in the same location of the sand, you start actually messing up with the structure of it, you know. So for either so you have to watch for this, because usually what would you do? You would just like lay them flat. That's a way to store them. Or we hang them by the arbor hole. But usually this one's is like this is actually kind of common sense. I wouldn't expect anybody to actually store the wheels like this, just because it's actually not the easiest way to store it, like just sitting vertically. So this is actually a common sense that I would say that's common. But this one's, I think that's where people would actually not do well on the decision. And then now you don't know what's the condition because you store it in the wrong way. And then now you can put somebody in danger. That can be you or somebody else. So we are not going to go uh, very in deep on types of wheels as of like for us, for us, we're always going to kind of use like a aluminum oxide. I don't think we're going to ever use a diamond one or a silicon one. But there are different types of materials, right? For us, I'm more interested in actually different types on the angle grinder side. But let's look at the types for the grinder, for the pedestal grinder. So if you look at the wheel, it has a code, and then you can actually, it's actually a standard of how the code is generated. So between material that's made, like at the grit, how hard the bond is. So like that means if I'm grinding something, what's the rate of that I want the grinding wheel itself to give out, so I don't clog it, you know. So this is the bond of all those like little sand particles or the aluminum oxide particles there. And what kind of bond is used? So I don't think that this matters as much as the difference between the grinding wheels as of use. So um, somebody told me like so for the project, some people they had to cut the metal straight up on the welding on the welding area there, just because the other equipment that we have for cutting the stock wouldn't be suitable to cutting the material that we wanted, right? So like either the sheet of steel was actually too thick, or it was too big, you know, too wide. So then like um, we wouldn't be able to use any of the other equipment to cut it. So like we had to cut it using the angle grinder. So if you look at the angle grinder, we can have several different kinds of wheels. So we have one that's called cutoff wheel. We have another one that's a grinding wheel. We have another one that's let's see, a polishing wheel. So they are actually, the construction of the wheels are different. So somebody once asked me, can I cut off with a grinding wheel? The grinding wheel, the thickness is kind of like this. The cutoff wheel, the thickness is kind of like this. So I would say, can you cut with a grinding wheel? You can grind all the material until it actually disconnect. So you can grind all the wheel until you did grind everything, and now it's just gonna break it off. You should do it? No. Why? Because the construction of this is actually to take material and polish at the same time. So you're gonna take, so you're gonna have to invest time and other resources there to actually accomplish this. And when you cut off with the cutting wheel, I don't know like if any of you guys actually use the cutting wheel for the project, but you can see how this wheel is gonna start to get smaller as you cut it, as you cut the steel there. So the wheel is gonna start to get smaller. So you start with a wheel that's like that, that with an initial diameter like that, and then you end with one that's like a half size. So the rate that the rate that my wheel is actually gonna give out is different than this one. So for cutting, we have to use the cutoff wheel, and for grinding, we have to use the grinding wheel. Can I polish with the grinding wheel? Uh, yes. Should you polish with the grinding wheel? No. Can I grind with the polishing wheel? Maybe. Should you grind with the polishing wheel? No. Not because like you can do it that you should do it, right? So I believe that like the difference on the wheels is actually more important on the for the grinder. I don't know why, but it's getting not moving here. Let's see. All right. All right. So how to throw a grinding wheel. So we can talk about like what's true, and I already talked about like what's being true. It's actually so your wheel is square. So if you look up online, my grinder is vibrating. How do you fix that? So and I already did that like in the past. You're gonna find a ton of accessories for actually balancing your wheel. So you pay like a $50 for a wheel balancer. A wheel balancer is actually something that you add here that has like different weights that you can move the weights around, so you can actually make that side to become balanced again, right? However, the price is very similar from buying another wheel. So I would invest in actually buying another wheel before I would invest into actually a wheel balancer. We're trying to cover up a problem, you know. We should just go ahead and fix the problem. And actually, the another video that's actually it's actually a problem, you know. So how do you know if the wheel is true? People would get the wheel. You'd actually install something on the wheel, like a bearing or something, and then you put like a onto something like this. So now, if there's one side there's more weight, your wheel is gonna go like this, and it's gonna have the side with more weight on the bottom. So as soon as you leave the wheel there, and the wheel never turns around, it says that's true. So like the mass is actually spread out, like in a constant way, you know, like it's all spread out. If there's one side that's heavier than the other side, your wheel is actually going to go and move, so the heavier side is on the bottom. And then you're going to see a lot of videos on the internet of some very smart guys that they would do what? So if this is the heavy side, they come with a drill bit and they drill on the side of the wheel. We just started the class saying never grind on the side of the wheel. And now there's a guy drilling on the side of the wheel to reduce the mass on that side. So then a guy would drill there, he'd put it back on the he would put in the back on the station there to test. Now there's another side, so he keeps actually drilling on the sides. You are messing up with the structure that the engineer designed the machine, and now again you put yourself in a condition that you might get comfortable, but it's actually you're setting up a trap for yourself. We don't know how the wheel is going to behave anymore. So the only thing that we do to the wheel to make it true is to dress. So the problem is if a guy come and grind on the side of the wheel right there, grinds on the side of the wheel right there, and now the wheel is actually not true anymore, what's the solution? You'd have to dress the wheel until the wheel gets this small. Oh, but I'm gonna lose a lot of material. You shouldn't actually use the side of the wheel. So that's what you get for doing what was wrong. So for us, you guys are not gonna have to dress it, but to dress, we just push the dresser against the wheel. If there are sparks, it means that the wheel is winning. So the wheel is actually grinding the dresser. So what do? Push it harder against it. And then if we stop having sparks and you go into having all this dust coming out, it means that the dresser is winning. The dresser is doing its job. Is dressing the wheel. And then, so we don't do what I told on the other slide. That's actually just dress on one side. We have to go back and forth with the dresser. So what you get is actually something that's flat in the front, right? So inspection of the wheels. You always look at the wheel to see if there's any cracks or nicks or whatever. You check the RPMs to see if they match. And we can do also a ring test. Let's see, I can actually add a video here of a ring test. And we can actually do one in class too. So if you hold the wheel by the arbor hole and you come, let's say, with the hand of a screwdriver and you hit it, it's gonna ring like a bell. It's gonna go like ding, and it's gonna like the wheel is like the sound is gonna be like a bell. It's gonna actually it's gonna continue. If you hit on the side and it goes like this, and the sound is just like a, it means that there is a crack on the wheel. So usually that's a good way of telling. So like you're replacing wheels. You can do a ring test. Usually we are not gonna actually take the nut out, take out the wheel, and do a ring test, and then put the wheel back in. You know, we know that we're not gonna do that. But usually when you're replacing the wheel, you find another wheel that was like a stored somewhere. Then you can do a ring test that's gonna already tell you like if there's a crack that sometimes you can't see, but there's um, a crack there. So run the speed at least at a minute um, before you actually touch it. So I want to add one more thing to the grinder, and then like if you guys have questions, you can ask. Um, so we do have a wheel for the grinder that's actually a steel wire wheel. If you guys don't know what's a steel wire wheel, it's a wheel that's a bunch of steel wires like this. What do you use that for? It's for like let's say something is rusty, you want to clean up the rust, but you don't want to take material out. So it's actually very common to use um, a steel wire wheel. However, so let's say this is the steel wire wheel. That's the center. And just like the other wheel, this is my rest. Again, again, as close as possible, right? But now, let's say I have a piece of a 1/4 inch round stock, and I'm gonna apply it right here. Even though this gap is actually the smallest that I can get, the piece of round stock on my hand is gonna be pulled in. Can you guys visualize that? Because it's actually gonna, as you push forward to actually clean it up, it's actually gonna get in between this the steel wires here, and then it's gonna be pulled down. So we have to have extra, say it again, extra, say it again, extra attention when using it. I'm not saying do not use. Engineers, they do difficult stuff, and most likely you're going to be working with something that is not that's not the safest. However, your training is going to allow you to do things safely. So that's the same in this case. We just have to be like we have to pay extra attention so we don't put ourselves or somebody else in a bad spot, right? Does anybody have any questions about like the grinding wheel or the grinder, or if Jim has something to add?
I'm good.
Right, so let's try to jump into the saw. So for us, we have a couple of bend saws there. A bandsaw is called a bandsaw because the saw itself is actually just a big band. The difference between the power hacksaw is actually the power hacksaw. This is the blade, and this machine just keeps moving the blade back and forth. While that one is just like a rotating in one way. So that's the difference between the hacksaw and the bandsaw. And the bandsaw, we can have a vertical bandsaw or a horizontal bandsaw. Kind of like pretty straightforward. So these are the machine tools. But the idea is actually very similar to the saw itself, to any hacksaw or a reciprocating saw, you know. So, for example, here, the throat, we have the throat here, and we have the throat right there. Is actually how much you can actually put it in. Right? Why is that important? For example, if I'm cutting something that's this big, if I'm cutting something that's this big, I won't be able to cut it all the way through if we don't change the direction. See? So the throat is gonna dictate what's the depth of like the max depth of what I'm gonna cut. Right? So another thing that's very important is actually the blade type. So my idea is instead of actually looking at some like a technicalities, I want you to kind of like to have an idea of the blade type based on common sense, right? Okay, look at the common sense. And then you're going to see why a different blade wouldn't work. So if we are using a hacksaw, then you kind of know that the hacksaw is made for metal. A hacksaw has the teeth like this. That means more teeth per inch. If you look at the teeth itself, the height of the teeth is actually smaller. That means for every stroke, I want to take just a little bit of material several times. I'm not looking at volume in one per one teeth, but I'm looking at volume per several teeth. So that's why I have more teeth that has a smaller height. So that goes for not for metal, but for harder material. Which metal is compared to wood, for example. If I look at a saw that's made for wood, so like a woodworking bandsaw, the teeth are going to be kind of like this. Oops. So I'm looking at a smaller number of teeth per inch and higher teeth size, height. Why is that? Because the material is soft enough that I can cut, that I can cut more material in only one pass. What if I try to use a big tooth with a harder material? I have a piece of like metal there. I come with a wood saw here, and I try to run it. If I'm running by hand, I won't be able to do it. If I run with a machine, I'm either going to damage my blade or my machine. So that's the very basic thing, like a harder material, smaller teeth with more tooth per inch, softer material, less tooth per inch with like a bigger teeth, right? So now something that we can start thinking about is, so imagine that this is the blade. Now I'm going to come and look from the front here. So this is my blade. Now I can talk about, okay, if the material is super hard, I have to change the width of my blade. Because even though I'm going to make my teeth super small, a super small teeth with a very wide blade, I'm still going to take a lot of material, right? So now you can think of also the width of the blade, right? But now let's look at something else. Like I want my blade when I'm cutting here. So imagine this is my stock. Once I'm done, I want a gap like this, right? But my blade can't be that wide. Why? Because otherwise I'm going to try to remove too much material at once. And I can't make my tooth smaller. So I have to make my blade thinner. So how do you make sure you take out this width of material when you run the blade? So now you can have teeth patterns. So if you look at any blade, or some of the blade, or most of the blades, if you look at the blade right there, I think there's gonna be a picture later, but like it's very common that you see like so now let's see, I'm gonna look from here, right? See, that's B, that's view B. So you can see one tooth on this side, one tooth on that side, one tooth on that side, and then one tooth on that side. So like see, this is the blade, but you have some teeth going on one side, the other teeth going on the other side. So once you run the blade, this is what's gonna happen. You'll take some material from this side, and then once the next train of teeth gets there, you're gonna take that side. See? This happens because you have to actually maintain the number of teeth touching the work in a certain way so you can complete the cut. So you have, let's say, we have this bimetal blade. For that to cut steel, you have to cut at this rate. But you have to have all the time so many teeth touching the work at once, you know. So then you have all these different variations of teeth, so you can accomplish that. Right. So now we're going to talk about the type. Usually, pretty much all the ones that we have are bimetal or flexible. But I would say bimetal is actually a piece of steel that we actually do like some heat treatment, and then now we harden it, and or we actually do like an alloy, and we actually harden it so we can use it. However, for some material, we will have to go into saying the material is so hard that I need a carbide tip. So the carbide is actually that same one that we use on the lathe, on the mill. And what do we expect from a carbide tip? It's brittle. So we just have to watch for that. We have to know, like, oh, but like which one? I don't know. Usually for buying the blade, I would say what blade is used for this material, and then I buy one and I have it there in stock, you know? So like because there are different ones, and each one you have to use them in a different way. Right? Pitch. So we were talking about width. We talk about um, we talking about offset. Offset that we talking about was the thing about like having some teeth to the right, some teeth in the middle, some teeth to the left. So that's what's called offset. So see, raker would be one tooth to the left, one tooth to the right, one tooth in the middle. Wavy, three teeth to the left, three teeth to the right. And straight is actually only one tooth on each side, right? So that's what we're talking about, like on this slide right here. So this is the offset. But pitch, I mean, sometimes when I start cutting, I want to have teeth closer together. And then as soon as I move a little bit, I wouldn't mind having teeth that are different. And then now, so it's not going to be exactly like this, but like just the idea is I'm changing the specs of my teeth even within the blade. So that would be my variable one. Why is that? Because for that specific material, somebody that was doing an analysis said, this is actually the like for let's say for manufacturing, this is the best blade that you can get. It's a constant blade because you have this machine that only do this cut in this type of on this type of metal. So this is not going to apply to us. Usually ours is just like 1. Why? Oh, I need one that's going to be for aluminum. I need one that's going to be for steel. I need one that's going to be for wood. So that's pretty much like a straight up like a tip for people that just like us, like at home or you marry. So this is what I talked about. You want so many teeth in contact with the work. Why? Otherwise, if we have, let's say, this one, so I have a piece of wood here, and my piece of wood is like this, and that's my tooth right there. What's going to happen? This guy's going to push my wood. My wood's going to do this. It's going to chop. It's going to shear right there. What's going to happen to this? It's going to go and tuck. So if you're cutting something and your material is like, there's a chance that like you just have too many teeth, like too few teeth like in contact with your work at all the times. So this analysis is actually more important in for example in a manufacturing environment. Why? You are trying to maximize the speed, or like you're trying to maximize the efficiency of your process. So you want the best blade for that very specific piece of metal that you're trying to cut, right? So also when you're talking about the pitch means the distance between the teeth is if my material is actually very soft, I want a higher pitch. Why is that? Because it's going to be, for example, if my teeth are so small and I'm trying to cut aluminum, it's going to be easier for the aluminum to get caught here. Just because aluminum is so soft. But if you're trying to cut like something that's so hard, even if you try to cut like a piece of like let's see, um, a piece of iron with this blade, you are only gonna kind of like scratch the surface a little bit. So all these little particles here that are coming out, all these chips, they're not gonna be enough to actually clog this. So what's gonna happen? As soon as you run, all these particles are gonna come out. All these chips are gonna come out, and they're just gonna fall off because there's not enough for one piece that shears off to actually go and fit exactly right there. So we have to understand about chip clearance based on if the material is actually harder or softer. So shape of the teeth, you can have different kinds of shapes. Shapes could be like this. It could be like this. That's very specific to the, if you buy a very specific blade for a specific material, right? For example, I will never have this shape when cutting metal. Why? It's gonna get stuck here, and I'm gonna shear the top of my teeth, you know. So then you want something like this. I'm gonna come and take some material out, take some material out, you know. We'll go. Right? So when we use a saw to actually increase our efficiency, we have to change to match the blade to what we're cutting. Always cut to the one side of the inscribed line. So this one is actually something that we touch up, especially on an ENR 280. And 281 is like, imagine I want to cut a piece just like this from this piece of stock. And then I put it here on top, and then I get like a marker, and then I mark this. Because the tip of my marker is kind of wide. Where should I cut it? If you cut on this side of the line, your piece is going to be too short. If you're going to cut on that side of the line, your piece is too wide compared to the other one that you want to do the same. If you cut it in the middle, you're still too wide. So usually when doing the layout, we try to scratch. So just, it's a very thin line. And now you have to understand, am I going to actually put my blade on that side or on this side? Because the material that I'm going to take out, so this is what's going to come out, has the same width of the blade. Right? Then we're starting time. So, and actually using the same idea, we should not use a new blade on a node cut. Imagine you start cutting something. So I want to cut this piece here. If I'm using a node blade, the blade is this thick. Why? Because it's old. It was already like worn out. So you start cutting it. As soon as you, and then the blade would break or something and you have to replace it. The new one is this wide. So that's why they say not to use a new blade on a node cut. You turn it around and cut from that side. Right? All right. We're short in time, but like